together with Hexagon FTI. We have been collaborating for many years. Some of you are already using the software. So, in today's webinar, you will learn how to identify the cost for a component in an early phase, as well as identify the geometrical issues so we can reduce changes in an advanced phase of the project. About myself, I'm Luisa Diaz. I'm business development. I represent FTI in South Europe. And I will be doing the introduction for about during 15 minutes. And my colleague, Mikey, he's lead application engineer at FTI. Okay, so let's start. We'll see how using FTI solution to create value analysis and value engineering in your organization. So the agenda for today will be an introduction. I will tell you who we are. After we will talk about what is continuous improvement and value analysis and value engineering. We will talk later what is material cost relationship also to the total cost of the project. And later on, Mike Lee will do a demonstration of our solutions into CATIA. So we'll be showing you cost optimizer. So using cost optimizer, you can develop optimal blank shapes and also coil nesting to lead to substantial cost reductions. At the end, we will leave time for you to ask questions. So if you have questions, you can write down and ask questions at the end. Okay, about us, FTI was born in 1989. It was a spin-out of an excellence center created by the Canadian government. It was composed by a lot of people with a lot of experience in sheet metal and costing. So FTI now is an industry standard technology for costing, design, and early feasibility for sheet metal components. We help manufacturers to reduce costs on average of 3 to 5% per program. Also, we help to decrease engineering changes in an advanced phase of the project if you use the software in an early phase. So now FTI is used by 21 out of the top 25 automotive OEM in the world. You can see here who are our customers. So, of course, we are into the automotive industry, but not only, we have also customers in aerospace and any kind of manufacturer working in sheet metal, Tier 1, Tier 2, etc. I want to talk to you mainly who is using our software. We have a very high presence in these three groups. The first group is cost engineering. So people working in quotations can benefit a lot using our software because you can have the blank, and you can discover in a very quick way how much it costs your blank, and you can have an optimal configuration of your nesting. The second group is design engineering. So if you work as a designer using CATIA in this case, you can use our solution into CATIA to have the feasibility of the part, and this is very important in the very early phase of the project. Also, we are in the manufacturing engineering group. So in this group, we use a solution called Streamline Development. It's going to tell you step by step how it's going to be your Streamline Development. So today we will focus more in the first and the second group. But if you have questions, do not hesitate to ask us. Okay, what is continuous improvement and value analysis, value engineering? For us, the continuous improvement is a way of working, is how we use It's how we work in every day. So we are continuously modifying things. We are continuously taking out new features in our software. We are continuously, for example, listening to our customers. So all the features we take out is to satisfy our customer needs. So this is in contrast of thinking like if we have been working every day in the same way, why we need to change. So for us, it's not that. For us, it's we are all the time up to date with our technology. Also, regarding value analysis and value engineering is a problem-solving methodology that uses two effective processes to optimize the value of a product or service. So value engineering, value is all the things we do in an early phase of the project before any significant financial investment. So for us, it's very important to give us a value to the engineering we do in that moment. For example, if we do a quotation and we have done all the process, you have been working with our software, you can have the feasibility, you can know how much is the price, so you can make sure that your quotation is going to be okay, and you will be following all the steps, so you will not have surprise maybe at the end. Value analysis is all the things that happen after the product development. So it focuses more on existing product or services. Both of them are to improve the value. In here, we can see the relationship of the cost for a sheet metal part in comparison with the total cost of the project. So you can see the total cost is divided in labor, purchase materials, sales and administration, etc. So you can see here also from the picture, you can see that the bigger cost part of the cost is the material. So the material can be can represent from 55% to 70% of the total cost of the project. That is why, because for us it's very important to reduce the cost in the shield, in the metal, in the parts of the metal. Sorry, because we will be acting directly to the 70% of the total cost or the total cost of the project. In here, you can see three kinds of nesting that we can do with our CATIA solutions. For example, the first configuration, you see that our material utilization is 69%, and the weight is 4.9 kilograms. So you can, in comparison with the second configuration, for example, the weight increased a little bit because the material utilization is decreasing a little bit. And the last one is the best one because we have 82% material utilization, so the weight is reduced to 4.23 kilograms, and consequently the cost is going to be less. Okay, and now I will leave the screen to Mike Lee, who will be doing the demonstration into CATIA. Maybe later on we will come back a little bit to the presentation.
Can everybody hear me?
Yeah.
Oh, perfect. Okay. So hopefully you can see CATIA right now. Thank you, Luisa, for that introduction. What we're going to do is we're going to look at the application, so our cost optimizer within CATIA V5, and we're going to look at a demonstration on how we can calculate all of those costs relative to the material. We'll look at various configurations in nesting, and we'll show you how quickly you can get all of those results. So in this particular example, we're going to look at a rail component, typically used within your door frame to help raise and lower your window. So in this case, I have a solid model, which you can see here. And the way that we perform our analysis is we require a surface model representing one side of material. So what you'll see within the process is I spend a lot of time doing things within CATIA. So I'll be doing functions within CATIA in order to prepare my model for my analysis. All of the tools that I'll use from FTI are all fully integrated into the CATIA environment, and you can see all of the icons here on the right-hand side. So I'll have all of my nesting icons, my costing parameters, my unfolding tools, blank development tools, as well as my springback tools. All of the functionality is fully integrated in CATIA. So what this means is I never have to leave the CATIA V5 environment. And also what it means is that my model and my analysis are associative and regenerative to itself. So if I make any changes to any radii, for example, as long as the model has been prepared parametrically, everything will update and show me that things need to be updated. So as I said, I start with in this case, a solid model. I've created a geometry set where I'm going to do all of my manipulations, let's say. So to start, what I want to do is I want to extract one side of material so that I can perform my analysis. So this is what I'll do now. Looks like there's a bit of a tangency issue here, so I can just use the multi-extract to pick out that surface. Say OK. And then I can also hide the 3D just to make it a little bit easier to see. So now I have the surface model representing the component. One of the things that we always like to look at when we're doing our analysis is typically we fill in holes that would be pierced in secondary operations. We can then map those hole features back to the part. FTI has created a tool to automate this process for you. So you could go in and use your CATIA fill hole function, fill in each individual hole, and then join the entire model back together. As part of our application within Cost Optimizer as well as CATstamp, we've created a tool called Fill Holes, which does that automatically for you. So basically what you do is you select the icon for the function, you choose the part, and then you specify that you want to fill the holes. You also specify the hole size. So we're looking at the perimeter of the hole. Any perimeters lower than 1,000 millimeters, we'll go ahead and fill in that hole automatically for you. We'll create the fill, and then at the end, we'll join it all back together. You can also choose the continuity that you want to use for those fill features. So I'll simply say OK. And then what you'll see is a fill is created in the tree for each feature, and then it's joined together. One of the other things that we like to look at when we are doing an advanced analysis is pre-curving the blank. So sometimes what you'll do is you'll start off by pre-curving the blank before you're forming it to balance the draw depths. So the way that you would do that in our software is first you need to create the binder surface, which represents that curvature. So again, we're going to look at using CATIA functionality. I could use this edge, for example, as the curvature, and I could extrude this edge and then extrapolate it to make it larger than what the developed or unfolded part would be. So again, using CATIA functionality, I can simply choose the extrude function, and then I can choose my directions as well as define my distances. So maybe something along the lines of this. So something like this. So right now, sort of in the X direction, I have a surface that's extended larger than what the developed blank or unfold would be, the flat pattern. I still also need to extend the ends to make it a little bit larger as well. And as I said, I'll use the extrapolate function. So I can simply just choose the edge. Let's just create an extract. And let's do it twice. And maybe we'll go, let's do 20. Generally, I like to use the curvature continuity. It just looks a little smoother. So what I've created here basically is an unfolding surface. So a surface that I'm going to use to pre-curve the blank. The other reason that I do this as well is when I do the simulation, I'm going to want to hold the part along this surface here with what we call a pressure pad or a holding force to keep the part from moving as we do the unfold. because the part is curved, I need to use a curved binder to make sure that it does the intermediate unfold to give me the proper length for the part. So right now what I have is a join representing the geometry that I want to analyze, and I've also created an extrapolate to represent the pre-curved surface, or what we call the binder. From there now we have essentially all of the geometry now that I need to perform my analysis. So then I come to this icon here called formability analysis. You'll also see that all of our tools are toolbars. So we have the formability analysis. We also have the nesting toolbar as well as the fill holes. So I select formability analysis, and everything that I need to perform my analysis will be contained within this dialog on the various tabs. So the first requirement is the part geometry. So I choose the part geometry. The join 12 will then appear in the dialog. The binder surface is optional. I don't have to choose it, but in this case, as I said, because of the curvature, we want to use the binder. So we can choose the binder surface, and then we need to specify the material type and thickness. So in this case, we can come down and we can choose a material. This is generally a mild steel or a cold rolled steel that's electro-galvanized because it's within the window. In the door frame, we want to make sure that it doesn't rust. So we can choose, in our case, a CR-EGDQ. So this would be a cold rolled electro-galvanized draw quality steel. We then specify the thickness of the part. So in this case, I believe it was about 1.2 millimeters. And then we need to specify the thickness direction. So this parameter here is quite important for our analysis, because when we perform our solution, we mesh the surface that we have defined here as the part geometry. And then when we go to solve, we offset that mesh to the neutral fiber to try to give you the best blank, most accurate blank that we can. So in order to do that offset, we need to know the direction of the thickness. So by default, the software always chooses middle, and the arrow would point in both directions, representing the direction of the thickness from the middle. In this case, we chose the top side of the part, so we need to use one of the sides. So it's either side 1 or side 2. So side 2 is pointing up, which would be the direction of the offset, which is incorrect. So in this case, we would choose side 1 to define that thickness direction. We've now defined all the parameters that we need for material. The material database, as you can see here, comes with approximately 200 different materials, everything ranging from, as I said, the mild steels, we have bake-hardened materials, we have aluminums, we have high-strength steels, we have dual-phase steels. So there's a lot of choice that is available to you within the database. If there are any materials that are missing, or if you want to make any changes to anything in the database, itself is fully customizable, which means you can add or edit any of the existing materials. The next tab is the process tab, and this is where we would define if the part is going to be drawn or if it's going to be formed. We would also define the forming direction. So is it, what is the direction of forming for the part? So this is very important because generally speaking, the part model is not in forming position. It's generally in car position. So we need to know the orientation for forming. We do give you a few options for this. You could pick surfaces. So we could create a line and pick a line. We can pick a planar surface and it will create the vector normal to that planar surface. There is also an auto tool, which allows us to, or allows the software to automatically define that vector for us. So average normal means we create a normal on every surface of the part and average them out. So the blue arrow represents that forming direction. We can also look at minimizing draw depth and minimizing undercut. Once we've defined the tip direction, we can also display various things like the undercut, the draw depth, as well as the draft angle. So for example, if I chose the draw depth, you can see, and generally I have to hide the geometry so you can see the color plots. But basically, if I can highlight here, you have your color bar, which represents your values for the draw depth, and then those color codings are put onto the part so you can understand what those values are. You can also look at things like draft angle, so it'll show you the angle relative to your tip direction, as well as undercut. So this would highlight any features that are formed beyond 90 degrees relative to that tip direction. And of course, our goal is to minimize undercut when we're defining tip direction. So let me bring the geometry back. We can also apply constraints. So if there was any fixities for your component that you were aware of before unfolding, you could apply those fixities. The next tab is called conditions. So these are manufacturing conditions that we're going to mimic as best as we can in the simulation. So the conditions that we have are blank holder. So that would be a uniform edge tension around the part that would mimic the effect of having an addendum and a draw ring for a drawn component. Tension is where we're selecting edges and we're applying an edge tension. We can also apply draw bead pressures to lines on the outside of the component, as well as a pressure pad. So in this case, I'm going to choose a pressure pad, maybe with a low, with a medium magnitude. And what that means is that the software is going to automatically calculate the value for the force based off of the ultimate tensile strength of the material. So for low, we look at about 20% of the UTS. Medium would be about 40%, and high would be about 80%. There's also, we can also override those values, just simply enter the force in here. The units that you use for your force are related to the options that you have within your CATIA environment. We also have a mesh tab. So this is where we can define the quality of our mesh. Good, better, best, have some predefined standards for the mesh. Otherwise, we could use custom, and then we could specify the parameters. And we use two parameters to drive our mesh generation, what we call a chord deviation and a mesh size. Chord deviation is a relationship or a ratio between the local absolute sag, so the difference between the true geometry and the mesh edge, and then the length of the edge. And what we found is we've done, countless benchmarks, and good and better generally for automotive parts are going to work really well in terms of balancing accuracy and speed. But then when we get into, maybe an electronic component that is, the size of your fingernail, or a very large automotive component like a body side, then you're going to have to customize those values either to make it smaller for the small part or make it larger for the large part. We also have two additional tabs. These are advanced tabs. KPR is particularly designed specifically for Class A panels, where we're looking at creating a certain amount of strain in certain areas. So things like hoods, where you tend to have low areas of strain, we want to make sure that we have a certain amount of strain in the part for dent resistance and things like that, and of course for buckling. And in that case, you define target points, contact points, and then the desired value for major and minor strain. The software will then go ahead and calculate the amount of deformation on the edge required in order to produce that amount of strain. Finally, we have also a tab called DFM, which represents design for manufacturability. So this is looking at the feasibility of a part. And as I alluded to earlier with the conditions, there's something called a blank holder force. And what the DFM does is it's going to run a certain number of solution increments depending on what you enter here. And it's going to break up those solution increments into percentages of the ultimate tensile strength of the material for forces to look at various solutions for your blank holder force to try to calculate for you what is the best value to use for that blank holder force. Because one of the biggest questions that typically comes from the conditions is, what value do I put here? So DFM will help you calculate what that blank holder force value should be. So once I've defined all of my parameters, and of course you can see as I'm explaining it, it is a little bit slower, but we enter all of those values and then we're going to choose OK to run the solution. So I'll say OK, it's going to mesh the part. It is then also going to run our solver. And then once the solver is done, a dialog is going to pop up asking me if I wanted to start to display various results. So within CADStamp, because it is our design solution for design engineering, we do give you all of the options for things like the forming limit diagram, major strains, minor strains, so we can look at all of the early feasibility of the part. So as I did before, I'm going to have to hide the geometry. This is our deformed mesh, which represents the part. And then basically I can choose things like display the forming limit diagram, which is going to show me areas that are safe, areas that are going to split based off of the values that or the analysis that I've just performed. I can also look at things like the safety zone, which we're going to then map the forming limit diagram back to the part, so it's really clear to us which features might be causing us problems. So maybe we need to put a little bit more relief in these areas here for the flanges. Green areas are safe. Gray areas represent low strain. Blue areas are areas where we might have a little bit of wrinkling. We can look at thickness strain. So again, same idea. We're looking at what is the percentage thinning. For numerical plots, we do have the option to display the min and max values. We also can do what we call the pick info. So if I choose the pick info function, I can hover over different areas of the part and it'll show me the exact value there. If I then say enable multi-pick, I can pick a point on the part and then it'll stay there. And then I can go to another area and pick another part. So there's a lot of tools that are available to you to look at and evaluate the formability of your component or the feasibility at an early stage. So it's really good for designers to look at, am I making a part that is manufacturable? And of course, if we are designing parts that are manufacturable, we are going to reduce the number of engineering changes, which is then going to reduce the overall cost for the component as well as the time to deliver that component to market. So I'm just going to close this dialog. And then next, we can look at creating the blank from our analysis. We can also do springback analysis as well. We're not going to touch on the springback right now. We're just going to go into the blank development and the costing through nesting. So understanding your material costs. So blank development, the dialog, again, very similar to what you saw from the forming analysis. In this case, what we need to do is we need to link the blank development to a forming analysis. So we need to choose which forming analysis we're going to calculate the blank from. We're going to create the blank either on the flat or on the binder. We're going to create it as a surface or a wireframe. We can create the blank with or without holes. So we have those options. And then finally, we have an option for how we want to smooth the boundary of the blank. Do we want it to be a B-spline? Do we want it to be lines and arcs, or do we want it just to be lines? You also have mapping capabilities, so we could map features from the blank or from the part to the blank. So we can do that. We could also calculate the part weight as well. You can only do one at a time in terms of mapping or the part weight. So for the mapping, let's just choose this boundary here, just so we have one edge so you can see how the mapping works. Then we'll choose OK. And we're going to create a blank face feature with the mapped entity on the blank. So you can see that here. So this is now a surface that is associatively linked to the analysis. So if anything changes within the analysis, blank would need to be updated as well. So to look at the costing parameters or to understand what the material cost is, we need to define some parameters. And we have this dialog here called cost parameters. And what it does is we need to first specify the thickness. If the model was made using a shell command or a thin parts attribute or a thickened part, that would be automatically entered. We also need to specify a base material cost. So we can come in here, we can put in a value for the base material cost per blank or per kilo. We could also create a variable cost versus coil width table if we needed to. We can specify things like extra material costs, scrap values if we knew those, anything we can relate on a dollar per blank basis, which would be called consumables. You're going to want to enter whatever your production volume is. So maybe this is something large like 500,000. And then we can get into some costing for the blanking die. So we could put in if we were a die shop, we could put if we know how much it is to create a blank die based off of the length of the blank, so per unit length blank, we could enter it here. So die cost per length 1 means for a 1 out, per 2 means for a 2 out. Or we could come in here and say, okay, we know what our cost is going to be, and we can specify what that tool cost would be. So maybe the 1-up blank die would cost 15,000. Maybe the 2-up blank die would be more, but not double. So maybe it's like 22,000. And then if we were going to do cutoff tools, what does that cost? And then we can specify what the currency is. I'm in Canada, so I'm going to put Canadian. Those values are then created in the tree under parameters. I guess I don't have it shown right now. And then we can go into the nesting. There are 2 types of nesting we offer. We offer the blank nesting for blanking dies. So what this option does is it looks at 1-up, 2-up mirror, and 2 blanks, as well as those standard sheets. Or in this case, this would be made more likely with the progressive die. So we would use our progressive nesting. So we choose the blank that we want to run the analysis for. If there was a second blank, we can do 2 unique shapes for both progressive nesting and for blank nesting. Then we're going to choose the type of layout that we want to solve for. So what we do is we do give you many different options. We have 3 for 1-out. It could be a side carrier or a double side carrier or a center carrier. For 2-up and mirror, we have the same, generally the same solutions. We have the dual center carrier. We have a nested center carrier, center inside, center side, all these different options. And to make it clear for our users, we've created a picture to show you what that layout would look like. So a 1-up side carrier would be, if your L was your blank, would look like this, where you have the carrier on the side. For a component like this, we'd be looking at a 1-out double side carrier. So we have a carrier on each side, and then we need to specify the length or layout parameters. So what is the distance between blanks? So in this case, we'll go with about 6.5 millimeters. What is the width of the carrier? So in this case, 12. And then the carrier to part distance. So maybe we'll do 7 mil. This would be the number of blanks. So we could change how many blanks we want to show. We can also apply angle constraints, width constraints, as well as progression constraints. So I'm going to apply a progression constraint of 106 millimeters because I'm going to define this first as a known layout, and I'm going to do the same thing for the width. From there, once I define these parameters, the software is going to try to maximize the material utilization for these parameters that I've defined. Otherwise, if I don't put any constraints, it will always try to maximize the material utilization. What I've done now is I'm trying to create a layout for a known process to give us the baseline cost. So I can come back and I can double click on any of my components, and then I could come back and I could edit. So if I wanted the blank to be vertical, I could come in here and put on my angle constraints. So that would be the layout angle. And I could put a fixed angle of, maybe 90 degrees, for example. And that should create my blank pretty much head to toe. So we can look at it from that point of view. We have now created it that way. Once we've created the layout, it gives us all of the information in terms of material utilization, progression, the values that we've used. We can also right-click on the object and create the table. And the table will then show us all of the calculated versions or options from what we've defined. We can look at various options when we're analyzing the cost or what is the best type of layout. We can easily come back into the table and we can change the type of layout that we want to solve for. We can do them one at a time only. So if we wanted to look at maybe reducing coil width, we could then come back and we would specify maybe a different coil width. We would also specify different layout constraints. So we can come back and we could change the various parameters that we're using for our layout. We could reduce maybe the carrier to part distance or the distance between blanks, and we can start playing with various solutions with how these various parameters drive our cost. So we can look here, for example, if we reduce the coil width and we reduce the distance between blanks, how does that change our material utilization? Once I'm finished my demonstration, Louisa will show you all of this summarized in the PowerPoint presentation. So we can look at this. In this case, we've just looked at one-up layouts. What happens if we want to look at a two-out layout? Well, there would be various options within our two-out. So first, we would have to switch everything back to automatic so that we can calculate those two-out layouts. Maybe we do want to keep the same width of the 689 just to see what that would look like, but we would have to remove the progression constraint. Then we could come back and we could look at maybe a two-out side carrier. So we would come here and we would say two outside carrier. So now it's going to nest two parts, same component. So it's not left and right. Two out means the same. So it will take a little bit longer because now there is a lot more options for the nesting solver to look at. It's going to try to nest those into each other. They're going to try to, of course, maximize that material utilization. The other option would be if we were looking at, in this case, because I have a constant, I've kept the same width, it's going to keep the blanks in the same alignment. If we took off the width constraint, now we can change the width and we can start nesting them even a little bit differently, but they're going to be a little bit offset. And again, you're going to see all of these various options within the presentation that Louisa is going to show at the end when I'm done. So we'll just look at this last one, and then we can look at one more configuration that we would have to create within the software. And then we'll go back to our presentation with Louisa. Another option that we could look at is what is if we wanted to create this part double attached? So what we mean by double attached is if we created a left and right component at the same time. In order to do that, I would have to go back and do some geometry manipulation, and I would have to essentially split on the flange and then mirror the component, join it back together, and then run through the same type of analysis. So I would basically unfold that double attached part and then nest that double attached part together as well. So it looks like it'd just be a few more seconds to solve this two-out layout. And then once that's done, we'll go look at the double attached option. So hopefully what you're seeing so far is the ability to look at different nesting scenarios and evaluate, what is the most cost-effective solution. So when we talk about cost-effective solutions, we're looking at that value analysis. We're looking at, what is the best utilization, what is the best, orientation, what is the best type of solution. So do I want a one-out double side carrier? Do I want maybe a two-out double side carrier? And then when you do two-out, you have various options. You would have, as I said, parts aligned, parts nested together. Then if we looked at double attached, now we're talking mirror parts. We're talking about a left hand and a right hand. And then all of these solutions are very quick to evaluate. So the way we position the software always is that the designer it's very easy for the designer to do all of these evaluations, understand the various cost scenarios, as well as understand if the part is formable. So the feasibility, we call that design for manufacturability. So are we designing parts that we can make? That production or manufacturing is not going to have any problems when it gets down onto their end of the cycle, the development cycle. Just a few more seconds here, and the layout will be solved. Okay. So here you have your new 2-out layout. And again, if there's more than one solution, they would be under the table results, and we can toggle through and see what those values would be. If we double click on any one of the results in the table, it will update to that particular layout. So the other thing that I was alluding to was the ability to do double attached. So the way that we would do double attached is, again, we would have to do some manipulations to the existing geometry. So we would have to take this geometry and we would have to create a plane. We would have to split. So we would go through the process of splitting the surface as well as mapping this edge and then mirroring it. Because of the time that we're at right now, it looks like we're about a quarter to the hour. I'm going to pass it back now to Louisa to sort of summarize in some slides all of the different layouts that you just saw.
Can you hear me now? Okay. As you can see here, this is the part that Michael has been showing you. This is a known process. And as you can see here, this is the first configuration that we have. The material utilization is 1.04%. And the reducing cost per blank is 0.01. For example, say that we have 100,000 parts. This means 1,000 euros reduction. Yeah, I prefer talking in euros, even if we can see here dollars. But we are in Europe. So, second configuration, in this case, we have 9.63% material utilization, and the reduce in cost per blank is 0.09. So in here, for example, we can have 9,000 euros if we have 100,000 parts. Okay. Another configuration, this one, it looks very good. So we have a cost reduction per blank. In this case, is 0.14. So if it's euros, we can have 14,000 euros reduction cost in this part. So if you do this for all your parts, you can imagine how much is the benefit you can have using our solutions. This is another configuration. In this case, we use double attached, as Michael showed you before. Yeah, this case is 0.02 euros in the cost reduction per blank, which is 2,000 euros. So it depends how you need, it depends of your needs. So you can use the software difference in different configuration. The best thing is you can, in a very quick way, you can do a comparison of all these configurations that I can show you now. Okay. Yeah, this is more or less what I wanted to show you. I think we can leave you time. If you have questions, you can ask. And of course, you can contact us through CATIA group. So you have here all the emails to contact. Yeah, you have questions, please go ahead.